Hey, welcome to the Vodcast on composition of trigonometric functions and their inverses. So I started off with this picture here that if you are in my class, you've seen plenty, which describes the relationship between angles and ratios, right? And this complicated function machine sort of view. So let's just talk about this for a second. There's two types of numbers in trigonometry problems. There's angles and there's ratios. So regular trig functions like sine and cosine and tangent. Also, watch this. I'm going to use this new found thing I found on the. Oh, no, it totally didn't work. Oh, watch this. Whoa! Yeah, sine and cosine and tangent. I know you're excited. Anyway, sine and cosine and tangent are regular trig functions that take an angle, and then that's the input, and then their output is a ratio, right? Inverse sine and inverse cosine and inverse tangent, like these, right? Those are functions that go the other way. Their input is a ratio and their output is an angle. Specifically, their output is one angle. So the output is one angle that has the ratio that is the input that is in the principal branch of whatever function it is. So the principal branch is different for each type of function. So if it's an inverse sine problem, then it'll be between -90 and 90, which is the same as -pi/2 to pi/2. But if it's an inverse cosine problem, then it'll be a u/r ratio that gives you an angle between 0 and 180, or 0 and pi. Now, arcsine and arccosine and arctangent, these are the ones that we've been learning about recently. That gives you, the input is a single ratio and the output is a formula that gives you every angle in the entire universe that has that trig ratio. So compositions of trig functions and inverse functions are, you might remember this word, composition of functions, from back in chapter 1. That was when we had problems like f of g of x, right? We had one function nested inside of each other. So an example of a composition of a trig function and an inverse function is something like this, sine of inverse sine of 0.3. So let's look at this picture here to figure out what this means. So 0.3 is the input to an inverse sine function. So that's saying that here's my inverse sine function. Its input is a ratio. So this is a v/r ratio. And I'm going to take the inverse sine of it. And then the output is going to be an angle. That angle is going to have a sine ratio of 0.3. So if I take this, one thing that I think that a handful of students are confused about is that this thing here, inverse sine of 0.3, I replace it with its answer when I evaluate it, right? So whatever angle that is, I don't know what angle it is, let's call it theta, right? Then this becomes sine of that angle theta, right? So then I have to take the sine of that angle. So what is the sine of that angle? Well, it seems like I might not know, except for theta was defined as the angle that has the sine ratio of 0.3. So I know that this is going to be 0.3, right? I'm going around in a circle here. It's just like f of f inverse of x. I start with some ratio, I do the inverse sine, I get an angle. I take that angle, I take the sine of it, I go back to the ratio that I started with, okay? This can be a little bit more complicated for different types of problems. If I have one like this, which is the inverse cosine of the cosine of 30. So this is one that's pretty similar. I start here, right? My input is 30 degrees. I take the ratio, find the u/r ratio that goes with it. Then I do inverse cosine and it brings me back an angle. So this would be the case where this is the ratio. And the inverse cosine of that ratio gives me back the angle that I started with. So this is going to be equal to 30 degrees. Good enough. But it doesn't always work that way when I'm going around the circle in that way. If I do tangent of 135, right? So again, I'm starting up here. I take 135 degrees. I put it into tangent. What comes out is the ratio that goes with tangent of 135 degrees. And let's actually think about that on the unit circle. That's the whole problem. Tangent of 135, on the unit circle, right? 135 is here. I'm going the same amount left and up. So that means that the tangent of 135 is -1. So this is saying inverse tangent of -1 if I evaluate tangent of 135 on the inside. Now, inverse tangent of -1 is saying give me the one angle in the principal branch of tangent that has a tangent ratio of -1. Now, there are no angles in the principal branch that are equal to 135 because the principal branch of tangent is from -90 to 90. So the answer to this problem would be, oh, it's this other angle. It's the angle -45 degrees because that's the angle in the principal branch that has a tangent of -1. So you can see that because we have this complicated, not invertible relationship, I can't always say that f of f inverse of x gets me back where I started. But in general, I can, right? So in general, we would say sine of inverse sine of x. When I go this way, right, like I did in this first problem, when I start at the bottom, inverse sine of x gives me an angle with that trig ratio. When I take the sine of that ratio, or sine of that angle, I get back to where I started. So this is always going to be x, okay? So this way, right, when I have problems like this, where the inverse trig function is on the inside, that's a less complicated problem, right? I don't have to worry about the principal branch because the last thing I'm doing is not evaluating the principal branch number. The principal branch is rolled in to the output of this inverse function. When I take the sine of that angle, I'm going to get back what I started. Okay. So this actually opens the door for us doing slightly more complicated problems, like the ones here where the types of functions that I have on the inside and the outside don't match. And we're still going to look at this picture here, which I have a copy of, but smaller. So what I want to do here is I actually want to think about a triangle here. Okay, so here's some random right triangle. If I say inverse tangent of 1/3, what this is saying is find me an angle with a tangent ratio of 1/3, right? So in a right triangle here, that's like saying that for some angle theta, the opposite side is 1 and the adjacent side is 3, right? So this is obviously not drawn to scale, but this makes sense, right? If this is some angle, the output of inverse tangent of 1/3 is going to be an angle with the opposite 1 and the adjacent 3. Now I can use the Pythagorean theorem to figure out this side, right? It's going to be the square root of 3 squared plus 1 squared, so this is 9 plus 1, so this is the square root of 10. Now, what this problem, sine of inverse tangent of 1/3, is asking you to do is to find the sine ratio of this angle that is the output to inverse tangent. That's this angle here in this picture, right? It's this guy, right? So what is the sine ratio of that angle? Well, I know all three sides to this triangle, so there's no reason I can't just write it. Sine is opposite over hypotenuse, so it's 1 divided by square root 10. So this is a little bit of a complicated problem. There are a couple more wrinkles that we need to iron out. So let's look at this next problem here. When I have inverse sine of -2/5, that inverse sine is on the inside. I have to now think about which quadrant inverse sine of -2/5 is going to be in, so that I make sure that cosine, when I evaluate it, is going to be in the right that's going to have the right sign. So I'm actually, instead of drawing just a triangle, I'm going to draw a triangle in context in the UV plane. So if inverse sine is -2/5, this is saying that V over R is -2/5. So great, here's V is -2, draw 5 over here. So this is a triangle that has V over R equals -2/5. Now I drew it over there, not because I just felt like it, but because the principal branch of sine is from -90 to 90. And I can think about this angle here, theta, right, being the one that is in that principal branch. It's between 0 and -90. I could not have drawn my triangle over here, even though it still had a V over R of -2/5, because this angle theta is not in the principal branch of sine. That doesn't work out. So this doesn't work. No, no, no. So if I look instead at the triangle that I drew originally, right, so V is -2, R is 5, and then if I think about this, I can use the Pythagorean theorem again to find the third side. So this is going to be the square root of 25 minus 4, which is the square root of 21. I now can think about the trig ratios. I know U, I know V, I know R for all the points in that, for that terminal, right? So if I want to evaluate the cosine of that, it's U over R, which is in this case going to be positive square root of 21 divided by positive 5. So the negative that I have inside the inverse sine does not necessarily carry to the outside if I have different types of trig functions that are not positive in the same quadrants. Let's look at one more example that I can do over here. Move this up a little bit. So I don't even necessarily need to have a number on the inside of the trig function, the inverse trig function that's in the inside of the composition. I could just have a variable. The thing that I need to do though is think about this as a ratio, like x over 1, right? So again, if I draw my triangle, I'm just going to draw a triangle like I did before. I know that I I have some angle here. Let's draw this angle theta, right? Cosine, inverse cosine of x is saying that the cosine ratio is x. Adjacent over hypotenuse is x. So adjacent over hypotenuse is x. Now I can come up with not a number for the third side, but I can come up with an expression for the third side. So this is equal to the square root of the hypotenuse squared, 1 squared, minus the leg squared, x squared. That simplifies the square root of 1 minus x squared. So let's look at that angle, theta. What is the sine ratio of that angle based on this triangle? Well, it's going to be opposite over hypotenuse. So the opposite side is that thing that I just calculated, 1 minus x squared, and the hypotenuse is 1. So this is true now. The sine of inverse cosine of x can be simplified to the expression 1 minus x squared. I think that this is one of these things that seems really bizarre, but really it's not that hard to do. And we'll be practicing it in class, and you should ask questions about it if it's a little bit confusing. And we're going to also be tying this into some other content about graphs and domain and range of inverse trigonometric functions and relations. So that's all there is. Have a good night.